Alright everybody, so this is going to be the last video for this chapter. I'm going to try to make this as quick as possible, so just bear with me here. If you have questions, of course, you can ask me in class. Alright, so just to give you some motivation for where this is coming from, well, there's really two things. One, this is going to be a useful skill in calculus for those of you that are taking it, either now or next year, or if you're here at school or in college. And it all comes from this. So let's say we have two fractions like 7 over x plus 7 plus 5 over x minus 4. Okay, you guys already know how to do that. If I ask you to add these two together, you know that there's a common denominator of x minus 4 and x plus 7. So we'd multiply the first by x minus 4 over x minus 4, and the second one by x plus 7 and x plus 7. So then that gives us a new fraction that is both over x plus 7 and x minus 4. And then you just multiply 7 with x minus 4 to get 7x minus 28. Multiply 5 with x plus 7 to get 5x plus 35. And if you simplify, you could multiply out the denominator, which we really hadn't done before, but let's say we did. And then the numerator would be 12x plus 7. Okay, so the whole point of partial fraction decomposition is to take something that looks like this and go all the way back and answer the question of, well, what two fractions or three fractions or however many we need were added that gave me this goofy looking fraction. Okay, and the purpose for finding those out, and you'll see this more in calculus, sometimes this is a little bit more complicated to deal with than looking at two fractions that look like this. Okay, this is a much more tamer expression than having this. And you guys remember how to graph. This is easier to graph, that's easier to graph. This is not as easy to graph. So, I mean, there's benefits to it, but right now all you need to know is that partial fraction decomposition is essentially taking a fraction that's been already combined with some other ones, and we're going to go all the way back to figure out what those fractions were that were added together. Okay, so what we'll do first is kind of some background information and some terminology that you need to be familiar with. Okay? Something that's linear means that the degree is 1. So things like x plus 7, x minus root 3, just x, etc. Each of these expressions is linear because the degree of x is 1. So you have a bunch of examples here of linear expressions. Okay? Now, we know what quadratics look like. We have x squared plus 3x plus 2, x squared minus 5, x squared plus 4. These are all quadratic because the highest exponent is 2. Okay, so here's where this is going to get a little bit tricky, but once you see this, I think it'll help you going forward. This can be broken up into a linear times a linear. Because if you factor it, you get x plus 2 times x plus 1. This one could also be written as a linear times a linear. Either you factor it or set it to 0 to figure out that the roots are plus or minus root 5. So you get x minus root 5 and then x plus root 5. Okay? This last one here, or anything like this, this is a special case that we call an irreducible quadratic. we know things are irreducible quadratics when the expression, the key is that they have no real roots. Okay? So if you tried the trick that we did with x squared minus 5 and set this equal to 0, you'd get x squared equals negative 4, so x is going to be plus or minus 2i. These are imaginary answers. Okay, so anytime you'd have imaginary answers from a quadratic, we call that an irreducible quadratic. Okay? So now, irreducible quadratics, linears. That's really all you need to know here. Well, and of course, quadratics. Okay? So before I actually show you how to go backwards and figure out those fractions that were combined, I'm going to go through the general rules, and then I'll just do a couple of examples with you. Okay? So first, here are your steps. 1. Factor denominator two if all linear factors or linear factors to a power then all you're going to use is a constant for the numerator. Okay? 3. If you have an irreducible quadratic, which we just talked about, and you're going to use a linear numerator for the setup. Okay? And we'll go through one very complicated example, just setting it up, not actually solving it, so you can see how all these rules work. Okay? So, let's say you have 11x squared minus 4x plus 7. And let's say we've already done a lot of work and we've factored the denominator and we get x minus 3 squared, 3x plus 1, and then x squared plus 4. Okay? So now here's how the decomposition works. First, after you factor the denominator, you look at all your factors and identify what kind of factor we have. Here we have a linear to a power. So we're going to use constants for the numerator. Okay? Here we have a linear. So again, we're going to use a constant for the numerator. Here we have x squared plus 4. And now, maybe I could factor this more, but if you set it equal to 0, you see that this does not have real roots. This is an irreducible quadratic. Okay, let me use different colors here. This is just a regular linear. And now this one here is a regular linear, but notice it's got a power on the outside. So this is a linear to a power. Okay, so we'll start with the green one. Okay? Whenever you, and we'll just go a factor at a time. So x minus 3 squared, what you do is you start with just one x minus 3. So x minus 3 to the first. And then you keep adding as many as you need until you reach the exponent. So if it was x minus 3 cubed, I would do x minus 3 squared, and then x minus 3 cubed. Okay? But here I only have to the second power, so I start with x minus 3 and then x minus 3 squared, and now I'm good to go. And since these are linears, or linear to a power, I'm just going to use a constant for the numerator. So I'm going to put in a variable, we'll call it a. There's my constant, and I'll call this one b. All right? Next scenario. I have a linear, just a normal linear. So all I need is one of those. So we do 3x plus 1 in the denominator. And again, since this is linear, I just need a constant in the numerator. Okay? Last scenario is an irreducible quadratic. So I need to throw in another fraction with an x squared plus 4 denominator. And because this is an irreducible quadratic, you have to use a linear numerator. So what we need to do is something like dx plus e. This is what a linear equation would look like, but we use variables d and e. And that's it. That's your setup. Okay? Let's try a couple more where we're just setting them up. We're not actually going to solve them. Okay? Let's just see if we can set them up. So, if you want to try this on your own, maybe pause the video for a few seconds and then see if you get it right. Let's say you have x squared plus 1 all over x minus 4, x plus 4, and then we have x minus 3. Let's say this is to the 4th. Okay, so if you want to go ahead and pause the video for a few seconds, see if you can figure out what the setup is going to look like. Okay, and if you've done this correctly, you should have 1, 2, 3, 4, 5, so you should have 6 fractions. 4 fractions for the x minus 3 denominator, and then 1 fraction for the x plus 4, and 1 fraction for the x minus 4. And here's what the answer is. And again, you just pick whatever letters you want. Usually the thing to do is to just go up alphabetically as each time you use a constant. For x minus 4, it's just linear, so you use a. X plus 4 is linear, so you use b. X minus 3 is also linear, so you're just going to use a constant, but you have 4 of those. So you're going to go all the way from 1 to 4. So x minus 3 squared, x minus 3 cubed, and then the last one would be x minus 3 to the 4th. Okay, so this is kind of a crash course of how to set these up. We're going to actually do 2 quick examples of how to solve these. Okay? So let's actually go back to the first example, since we already know what that looked like. We had 12x plus 7 over x squared plus 3x minus 28. Let's say we didn't know what fractions created that. Here's what we would do. First, you factor the denominator, which is x plus 7 times x minus 4. Okay, so now what you do, after it's factored, you take that fraction and you do the setup that we've been talking about. So all you do is look at the denominators that you have. You have x plus 7, you have x minus 4. These are each linear, so we just need one fraction for each of those. So right now it looks like some fraction over x plus 7 plus another fraction over x minus 4 is what might have created this. Okay? And again, since these are linear, we'll just call the top A and we'll call the top B. And now your job is to actually go ahead and find what A and B are. So to solve, the first thing you do is to multiply by the fraction that you see here. So if you take the entire equation, I'm sorry, I didn't mean to multiply by the fraction. Multiply by the denominator that you see here. If you multiply everything by x plus 7 and x minus 4, what that will do is cancel out the left denominator, leaving you with just 12x plus 7. On the right-hand side, the x plus 7 will cancel with the x plus 7, so you just get a times x minus 4. And then here, the x minus 4 cancels with the x minus 4, so you get b times x plus 7. Okay, so now what you do, you go ahead and multiply everything out, so you get ax minus 4a plus bx plus 7b. And at this point, you could factor out an x from the two terms that have an x. So if I pull an x out, that would leave me with a plus b. So that's what I did here. And then everything that's left, negative 4a plus 7b, that's the not x stuff. Okay? And now all we do here is now we compare coefficients. So on the left-hand side, and you don't have to set it up like this every time, but this will help you for the first example. On the left-hand side, you have x. How many x's? Well, specifically, 12 of them. On the right-hand side, you also have x. But in this case, you have a plus b of them. On the left-hand side, you have a constant, which is 7. Oop, let me call it constant. The constant is 7. On the right-hand side, everything that's not x, negative 4a plus 7b, that's going to tell you what that constant is. So you set them equal. So what this does then is give you a system of equations. You set a plus b equal to 12. You set negative 4a plus 7b equal to 7. Okay? And then you just solve the system. So either eliminate or use substitution, however you want to do it. I will multiply this equation up here by 4 and then add everything up, because then this will cancel out my a's. Then I have 4b plus 7b, which is 11b. And then I have 48 plus 7, which is 55. So then I get that b equals 5. And now you can quickly go back to the first equation. If b is 5, then you can see that a has to be 7. So this is actually pretty easy once you get it going. So then your final answer looks like this. 12x plus 7 over x squared plus 3x minus 28. When we decompose it, we had x plus 7, x minus 4. This was a, which we found out was 7. This numerator was b, which we found out was 5. Okay? So these were the two fractions that had to have been added together to get you this result over here. And if you looked at the first example we did, that's exactly what the two fractions were. Okay, so that's the basic idea of how to do partial fraction decomposition. Okay, we'll do one more example that's a little bit more involved, and then that's it. And then tomorrow in class and in Thursday in class, you'll have some time to work on this stuff. Ask any questions you have before you take your test on Friday. Okay, let's say we have 7x squared minus 9x plus 29 over x cubed minus 2x squared plus 9x minus 18. Okay, so first I'm going to try to factor the denominator. It's 4 terms, and if you try to group looks like you can take out x squared from the first two. Here you can take out a 9. So then, looks like the denominator factors into x minus 2 times x squared plus 9. So let me just rewrite the fraction. So I have some space to work with. And now I'll put the denominators in factored form. Okay? And now let's just go through this quickly. X minus 2 has to be involved somehow. This is linear, so we're going to use a. X squared plus 9, if we could factor it more or find real roots, then I would have more than just this fraction. But if you set this equal to 0, you know that this is irreducible quadratic. So since this is irreducible quadratic, now we have to use a linear numerator. So something x plus something. I'm using b and c because those are the next variables in the alphabet. You can use whatever you want though. Okay, and then we'll do the same thing we did last problem, which is to multiply the entire equation by x minus 2 and x squared minus 9. I'm sorry, x squared plus 9. On the left-hand side, then that just gives you 7x squared minus 9x plus 29. On the right-hand side, the x minus 2 cancels out, and you get x squared plus 9. And then the x squared plus 9 cancels out here, so you get bx plus c times x minus 2. And now what you do is just work on the right-hand side, multiply everything out. So then you get ax squared plus 9a plus bx squared minus 2bx plus cx minus 2c. And maybe you don't even have to do it with all those details we did earlier. So now we'll just compare coefficients. We have x squared, we have x, and we have our constant. On the left-hand side, we have 7x squareds. On the right-hand side, we have a, and we also have b, so that's going to be a plus b. On the left-hand side, I have negative 9 as the coefficient of x. So we have negative 9x's. On the right-hand side, look for your x terms. Here they are, negative 2b, x, and then cx. So we'll write down negative 2b plus c. On the left-hand side, our constant is 29. On the right-hand side, everything without x's would create the constant. So we have 9a and negative 2c. So write that down, 9a minus 2c. So here's the system that we're trying to solve. It's a 3 by 3, but it's not too bad because each equation only has 2 variables. So what I'm going to do is maybe solve for b in the first one. So I get that b has to equal 7 minus a. And then what I'll do is plug that into the second equation. So then I get negative 9 equals, if I multiply negative 2 with b, negative 14 plus 2a plus c. And if I clean that equation up a little bit, we get that 5 has to equal 2a plus c. And now I have these two equations which only have a's and c's. So I'll solve those first for a and c, and then I can go back and find b. So let me just write those out in the usual format. 2a plus c equals 5. 9a minus 2c equals 29. If you double this equation and then add everything up, the c's cancel. We're going to get 13a, and then 10 plus 29 is 39, so a has to be 3. If you go back, if a is 3, then 2 times 3 is 6, c would have to be negative 1. And then now that I know what A and C is, maybe I'll just use the first one. If A is 3, then B has to be 4. So see, it's not too bad. And now we can write our answer. Our answer was something over x minus 2 plus something over x squared plus 9. Here we have A, so that's 3. And then it was bx plus c, so 4x minus 1. And this is the decomposition for the last example. Okay, so that's it for this unit. Farewell. We'll work on some stuff in class together, and your test will be Friday. Bye-bye.